Well, hello, Blake, Daniel. Looks like we're finally ready, at least I'm finally ready to finish off our week of notes. Took me a while to work with this stuff, so let's see. Hopefully things will go pretty well here as we take a look at it. So this is 16.4. We're moving on, and we're looking at surface integrals. So let's go ahead and let's give a start into what we've got to know. So we're going to build on what we learned yesterday. So first thing, we're going to really talk about a classic surface integral. So if we have a parameterization of g of uv, that parameterization of a surface with a parameter that's domain d. So the domain is the actually of the parameter of the variables u and v. Then we know that our integral over that domain of the function f of x, y, z ds is equal to the double integral over the domain of the function parameterized by our g of uv, and then our ds there becomes the norm of uv, or the magnitude of uv, the vector uv, du dv. And of course that could be dv du. Just make sure you set up your correct you have to just make sure you put your correct limits of integration that correspond with u and v, depending upon how you set those up. Related to this, this is if it's parameterized. But what if it's not parameterized? And we are going to look at that. So if we look at one where we have it where it's not parameterized, where we just have essentially the function of a graph. So we've got x, y, and z, and we're going to express z in terms of a function of x and y. So in that situation, we have this. We've got our f of x, y, and then for z, we have expressed z as a function of x and y. So now we're down to two variables, okay, but we're not actually doing a parameterized system exactly. It's a little bit different than that. And we're going to get this factor here of the square root of 1 plus, that's the partial with respect to g squared plus the partial with respect to y squared. And if you want to know just where this comes from, you can see it. If you take a look in your book, in the notes here on 16.4, and you'll find this. It's actually explained fairly well. It's on page 983. It's actually, well, it's on the page with diagram with figure 14, and their formulas 8 and 9 is what it does. So what you see there is they start right up above formulas 8 and 9 with z being equal to the g, the function there, g of x, y. And then they look at that parameterization there, and then they go ahead and they calculate the tangent vectors, which you see there, because we don't know what, we know that that's for z, we have the partial with respect to x, we have the partial with respect to y. Then when we go ahead and do the cross product there, we get our normal vector, and then when we take the magnitude, we get that square root of 1 plus g of x squared plus partial of g of y squared, like that. So that's where we get this formula from. So it makes sense once you take a look at that, and you could go back and you could start this completely. So you could go ahead and once you express it like this, you could go and calculate this, but this is just a quicker way. We just know it's this, so we don't have to go through the process of calculating this. That's all that we're doing. We're just saving ourselves that time. All right, let's look at some examples. So 12, for 12, it gives us a theta interval going from pi over 2 minus 0.15 to theta pi over 2 plus 0.15. So essentially what we're doing is we're going 0.15 above and below pi over 2. So that's our theta region. And here's our phi region. It's basically pi over 4 plus or minus 0.1. And so that's the region that we have there. And what it asks us to do here on 12 is it asks us to, first thing it says is to sketch the small patch of the sphere whose spherical coordinates have those things. Well, we're not going to sketch the sphere. Okay, that's one thing we're going to skip that part of it. I don't think that we really need to worry about sketching the sphere. But then what we want to do is we want to use the normal vector that we computed back in exercise 9 to estimate the area. Well, you guys actually did this. You actually did number 9. Me, on the other hand, I didn't do number 9. So let's go ahead and let's calculate that. I know, Daniel, you told me you had some difficulty getting it, so this should really help you see how to get it. So let's go ahead and let's get that normal vector first for number 9. So looking back at number 9, what we've got there is we have this function given here. And by the way, what this is this is a sphere of radius 1. So we can see that. It's a sphere there of radius 1. And so we know that we're looking here, and we know that the exact place on the sphere we're looking at, the particular point that we're finding the tangent plane, we're finding the plane that is tangent to the point where we have theta of pi over 2 and phi of pi over 4. So that's our sphere there that we're looking at. That's our particular point. So this is what you should have done back in 9. So we have to find, and if you've done this, you can quickly kind of skip over this, but this is the first the tangent component with respect to theta. So holding the phi constant, we differentiate. So we get derivative of cosine theta, negative sine theta, derivative of sine theta, cosine theta, and then derivative of, with respect to theta here, this is just constant, so we get 0. So plugging in our particular point values, we get that our tangent with respect to theta is this negative radical 2 over 2, 0, 0. Now doing the same thing for phi. So holding theta is a constant. So we've got this cosine phi, cosine phi. We have the sine theta times the cosine of phi, and then negative sine of phi. Plugging in our values here, we get 0 here, because cosine of our pi over 2. Here we get our radical 2 over 2, and here we get our negative radical 2 over 2. So those are our 2. So now to get our normal vector, we get the cross product there. Our normal vector at that particular point. So plugging in here, getting our cross product, so we know we can look at this. We would have, first one is just 0. Next component, we have a negative 1/2 when we multiply these, but we subtract that negative 1/2, so, sorry, positive 1/2. Didn't see the negative there. Didn't see the negative here, actually. My pen was covering it up. So we subtract that positive 1/2, so we have negative 1/2. Then doing the last one, we've got a negative 1/2, and we actually just add that one. So this is our normal vector. Finding the magnitude of that normal vector, we would end up, our magnitude ends up being the square root of, so we would have 1/4 plus 1/4, so 1/2, so we have the square root of 1/2. So here's our setup. So we know since we're doing area, here's our theta limits. Here's our phi limits. And we have 1 for our f of x because we're doing a area. And here is we find the magnitude of our normal vector. So doing this here, that's going to be root 2 over 2 when we find the magnitude there. And this one here, with obviously limits like this, it's a calculator problem. I just put the D here because I didn't want to type these in again. But typing those in, punching in the calculator, we get an approximate value of 0.0424. So that's 12. All right, let's look at 16. 16, we're given this information here, and they ask us on these to calculate the integral for this particular surface over the function here, which right now our f of x, y, z is a pretty simple one. It's just equal to 1. So this defines our surface here. So what we're going to need to do here is we go to apply this, is we're going to have to use this formula up here. sorry, this one right here. So going ahead there, we know that the we'll have the double integral over the domain, and what we are going to have to use is we're going to have to use our, in this case, because of the way our function is, we're actually going to define our y in terms of x and z, because those are the only variables we're given here. We're given what y is equal to in terms of z, so we know x and z, we're given the regions here for x and z. Notice that. So the one that we're going to actually use and parameterize with the other two variables is y, because y is given in terms of z. So going ahead and doing that, I could have solved this for z, but that would have been more complicated. So it's easier to do it this way. And then now we'll take our partial with respect to x squared plus 1, that's our partial with respect to y, which is just going to be 1 squared, plus our partial with respect to z. So, and we have dz dx. So let's go ahead and let's substitute in. So first we get our partial of x, which is just 0. Notice this is our g of xz right there for y. And our partial with respect to y here for this one, I wrote that down. That's partial with respect to z. Partial with respect to z is negative 2z. So now I can go ahead and I can substitute in. So now I've got the integral, and I know I'm going to go, notice for x, it goes from 0 to z. For z, it's going to go anywhere from 0 to 3. And then I've got, and I could have also done x to 3 as well. That would have also worked. And then my f of x, y, z is just 1, but there is my formula there with my partial with respect to z substituted in and squared. Well, looking at this here, what I see is that I don't want to integrate this with respect to z. That's very messy if it can be avoided. And what it can be done here is if I can get a z as a factor out here, that would really make things much better. So what I'm going to do is I'm going to get that factor out there by integrating with respect to x. So integrating with respect to, if I change it and go with respect to x first, I've got this right here. Now I can integrate. So all I did was I just changed these and changed my limits of integration. Now I can integrate with respect to x. This can be treated as a constant and just get x times that thing treated as a constant, evaluated from 0 to z. Plugging in z for the x, I just get my value here, going from 0 to 3 of z. Now this becomes one that's easy to do with u substitution. So integrating this with regard with u substitution, I get 1/8 is my factor, and I'll get 2/3 times that 1 plus 4z squared to the 3/2 power, all evaluated from 0 to 3. So going ahead here, what I see is this is now going to be, notice if I multiply these together, I get 1/12. Substituting in the 3, I would get 37 here to the 3/2, and substituting in 0, I would get 1 to the 3/2, and so that's my answer. All right. So let's go ahead and now let's take a look at number 18. Number 18, I'm just going to go far enough to set it up. So 18, we're given this information, and we're going to have to essentially use the same kind of formula, except for now, notice z is given in terms of x and y. So now I am going to use the classic one where it's f of xy, g of xy, because this becomes my g of xy right here. This becomes my limits for z, and we will have to figure out our limits for x, and we will find that what we'll end up doing is, you can probably guess by seeing something like this in here, we'll end up switching to polar coordinates in order to make it easier. So, first off, my z is g of xy, which is going to be this 4 minus x squared minus y squared. So my partial with respect to x is negative 2x. My partial with respect to y is negative 2y. So now I can go ahead and substitute into my formula. So, down here. So substituting into my formula, well, I've got to get my magnitude of my norm. So my magnitude of my norm there is just going to be this formula here. So simplify and factor the 4 out, and I get this x squared plus y squared. That is what we'll replace with r squared when we go to polar. So now I can go ahead and express, notice I need to find my limits for x squared and y squared. So what I see here is, doing this, I could re-express this like that. So what I did is I multiplied both sides by negative to make these positive, and then that made this a negative 4, so then I added it to both sides. Of course, it flipped these signs around, and so this becomes r squared. So what I get is, I get 1 is less than or equal to r squared is less than or equal to 4, and that means that when I take the square root, r is just going to be between 1 and 2. So now here's my integral. So changing to polar, I know my theta is 0 to 2 pi. I know my r is 1 to 2. Here is my basic equation here. My x squared is r cosine theta. My 4 minus z, looking back at this here, so if I solve this for 4 minus z, if I subtract z from both sides, add that to both sides, I get 4 minus z is equal to x squared plus y squared, but that's just r squared, so I can just put an r squared in there. There is my value here where r squared replaces x squared plus y squared. I do have to have my factor of r, and then I have dr d theta. From there, the nice thing is your r squareds cancel, and you get, it's a little bit of, not the easiest thing to integrate. This isn't too bad because it's u substitution. This one requires power reducing identity. Sometimes can be viewed as a calculator one at that point, and I think you guys know what to do from there. Okay, 16.4, 11 through 19 odd. I will say that on, be aware that on number 19, you do need to parameterize that. You don't use the basic xy, g of xy. That one you just want to re-express. It is a sphere, so you want to re-express it in spherical coordinates. Okay, with that, have at it. Hope you guys have a great Easter weekend, and really have a chance to reflect on what we have in the Lord and what He did for us. All right, see you guys later. Bye.